things are getting more exciting because we have this powerful tool that lets us find the slope of a tangent line to a point of a function at any point. It's a function. It's called f prime of x. It is a function that tells you the slope of the curve. Because the slope of the curve is the slope of the tangent line to the point at the curve. So, here, and we'll call this the derivative. What is the derivative? The derivative is f prime of x. That's the derivative. That is what it is. That's called the derivative. That gives you the slope of the curve of the line, of the point. Right? So let's imagine this is f of x. So let's imagine all the tangent lines at these points. So I would imagine, hey, that's the tangent line, that's the tangent line, that's the tangent line, that's the These are all tangent lines to these points. And the slope of the tangent lines are values of the derivative. Now, notice that this is the slope of the curve at one point, at another point, at another point, at another point, and another point. So the slope changes. It always changes the slope. Okay. Let's do so if I take if I make a table of a function and its derivative f prime, and I would do it if I were to do the limit process. Because we know this is equal to the limit as delta x approaches 0. The change in y over the change in x. So, if I were to plug in x, right? And I would plug in, well, what's the derivative? It gives me the slope of your curve. What's the slope of x? 1. It's just 1. F prime of x would be 1. What about x squared? Well, remember we did that? We got 2x, right? What about x to the third? Well, if we plug in x to the third into this equation, f prime of x is going to equal 3x squared. And if we plug in x to the fourth into this equation, it's going to get nasty. But we get 4x to the third. And then I'm going to ask you, what if we just plug in x to the nth? What if we just plug in x to some power n? Can you see a pattern here as we go along the function and its derivative? Do you see a pattern? I know for sure that these numbers match. That's all I know. And that this number right here is a 1 less than the number in front of them. Wait, so if I see the number here, and if this number is 1 less than that number, therefore if f of x is just x to any nth power, then the derivative is nx to the n minus 1. I just saw a pattern, so I don't have to do this anymore. Okay. And this is called a simple power rule. I'll put it up here. So, this is called the simple power rule. And I'm going to introduce different notation. F prime of x can also be written as dy dx. You can write it as dy dx. So, and this is fun because it makes the pronunciation, the derivative of y with respect to x. The derivative of y with respect to x. Oof. The derivative of any x to n and nth power with respect to x will give you this. Okay. So the derivative of this will give you this. No more. And why is this? Well, this is useful because if we have f of x equals x to the 99th power, or the 100th power, instead of doing this part over here, no one in the right, it'll take you forever to expand this. Forever. Instead of doing that, you could just use the simple power rule. The simple power rule and say, wait, f prime of x would just be 100x to the 99th. Follow that. Easy peasy. Nice. There is more rules we get introduced to. So here are the differentiation rules. We call it differentiation. The process of finding the derivative is called differentiation. Okay? These are differentiation rules. So, if I take a derivative of a constant, c, that's 0. If I take a derivative of a constant times an x, that's just, you can take out that constant, take a constant times f of x, we can take out that constant and replace it with just c times the derivative of x. If we take the derivative of some function x plus another one, we can actually separate this. we can separate derivatives by addition and subtraction. And that's it. That's your differentiation rules, as far as it goes. Okay? Sadly enough, there's no separation by multiplication or division. It just gets worse. So let's do some differentiation. Let's say f of x equals x squared plus 2x plus 5. Okay? Find f prime of x. Well, hey, that's just simple power rule. We can differentiate each one by addition. The derivative of the first one, by simple power rule, is just 2x. We can use simple power rule and the fact that we can take constants out to differentiate that. That's just going to be 2. The derivative of a constant is just 0. So we have that. That's the derivative. Easy enough. Okay, let's do another example. Okay. Can we find the derivative of this stuff? Well, this is a function over another one. Can we simplify it? Yes, we can. We can divide out, remember? So this is 1 plus 2x. Whoa, this simplifies to 2 over x plus. Wait a second. They still don't have. They don't. There's something wrong with that. We can't take a derivative. There's no rule. We'll make it into something that we have a rule with. So that's just 1 plus 2x to the negative first power. Ooh. Minus 5x to the negative second. Now we can do it. Because now we can use simple power rule to do this. So dy dx equals constant 0, times negative 1, minus 1, negative 1 minus 1 is negative 2, plus 10x, multiply that, minus, negative 2 minus 1 is negative 3. That is your derivative. Okay, let's do more examples of finding derivatives. Right now we're just finding derivatives. Okay. Square root of x plus 2x. Can we find f prime, the derivative? Okay. Wait. We can rewrite this as x to the 1/2 power plus 2x squared. Hey, now we can do that. Simple power rule. It's 1/2 x to the negative 1/2 plus, or x. That's a derivative. I keep stepping on these things. That's your derivative. Okay, so let's do another one. Let's differentiate this. Well, this doesn't look like any of my rules. Let's write it as a rational exponent. We can simplify this even more. This is being negative 7 halves. So this would be 3 halves minus 10 halves. So that means f prime of x would be negative 7 halves x to the 3 minus 1, that's going to be negative 9 halves. And that would be your derivative. Okay. I think we had good enough practice with all these rules. Now we're going to cover the trig rules. So let me erase this part. I'll keep simple up here. Okay. There's a derivative of every single trig function. All 6 of them. Okay. The derivative of sine x. This is a shocking one. It's cosine x. Wait a second. That means, people are like, oh, who cares? What does that mean? Well, think about this. This is sine. The slope at that point, at that x value, is the cosine of x. The slope of sine x at any point is cosine x. That's kind of weird. There is a proof, it's not that hard. Using the special limits. Just put cosine x here. So it's not x here. The derivative of cosine x, ooh, but that's a negative sine x. The derivative of tangent, secant squared x. The derivative of secant x equals secant x tangent x. The derivative of cosecant x equals negative cosecant cotangent x. And finally, the derivative of cotangent x is negative cosecant squared x. There is a pattern to it. Basically, all the cofunctions have negative values. Co have negative values. And this is secant tangent x. Cosecant is cosecant cotangent. The cofunction of negative. Cotangent is similar to tangent.
Hi, Jossie.
Is similar to negative cosecant cotangent. So these are all the trig rules. Just right, trig derivatives that you have to memorize. You have to memorize it. So let's practice. So if you have this, the derivative would be A. The derivative of sine is cosine. Oh, we got simple power rule. It's 14. That would be a derivative. Okay. What if we had let's see. What if you had that? Sorry. Well, you can simplify that, right? We can say that this equals sine over secant cosine over secant. Now what's secant? Secant is 1 over cosine. Sine over cosine is tangent. Cosine over cosine is 1. Wait, that means the derivative of this, is secant squared x and a plus 1, 0 from the power rule. That's it. That's all you got. 22 minutes, huh? So memorize those. Okay, so the derivative is special because it has a meaning. And its meaning is what? What is the meaning of the derivative? In terms of its meaning. So it means one thing. Slope of the curve. Okay. The other meaning is instantaneous rate of change. How do I spell this? EOS rate of change. It has two meanings. Instantaneous rate of change, slope of the curve. So, visually this would look like that. But what instantaneous rate of change? What is that? Let's talk about that. So imagine you were driving a car. Okay? So you're driving a car and you're moving what? You're moving 50 miles per hour. And then in 5 seconds, you're moving. So you're moving 50 miles per hour. Recorded at 1 second. So 50 miles per hour, this is time. Sorry. Position. This is your position, and that's your time. So at 50, at 1 second, you're at 50 meters. At 2 seconds, you're at 60 meters. Your average rate of change would be the slope right here, with that line. So your average rate of change is f of 2 minus f of 1 over 2 minus 1. That's your average rate of change. Okay? What would that be? That would be 60 minus 50 over 2. That's 10 over 2, 5 meters per second. So your average rate of change is 5 meters per second if you're driving a car. Now, if you are constantly changing your position, if you're constantly changing your position, if you were constantly changing your position and you wanted to know at 1 second how fast you're moving, at that moment of time how fast you're moving. So remember, your average rate of change is that's my average speed, I guess, from what, 0 or whatever that point is, from 1/2 to 3/2. That's my average speed from 1/2 to 3. But if I want, that's my delta t, that's my change in time. If I want my average to be almost exact, I want my, instead of average, I want my instantaneous rate of change. My delta t would approach 0. So at the instantaneous moment of time, it would be x prime of 1. X prime of 1. The instant, at that instant, at 1 second, right there, how fast am I? At that moment, how fast? That's my instantaneous rate of change. And that's the general interpretation of the derivative. I'm running out of time. So, there you go.